2, 1, 0. Liftoff.
No spacecraft had ever survived what Parker was about to attempt. Not because the technology didn't exist, but because for 60 years, nobody could build a shield capable of sitting inside a star's own atmosphere. Then, on Christmas Eve 2024, NASA did exactly that. And what the probe sent back didn't just confirm what scientists expected.
The amount of clarity and the amount of details that we got from Parker Solar Probe is totally unprecedented.
It contradicted assumptions physicists have held for decades.
Parker Solar Probe is opening our eyes on a new reality about our star, the Sun. It is rewriting the textbooks for us.
This is NASA touching the Sun, and the data it sent back changes everything we thought we knew. Christmas Eve, silence. December 24, 2024. Mission Control at Johns Hopkins. Applied Physics Laboratory goes quiet. Not celebratory quiet. The kind of quiet where people stare at screens that aren't showing them anything useful. Because the spacecraft they've spent decades building is now 94 million miles away, flying directly into the atmosphere of a star, and there is absolutely nothing anyone on Earth can do about it. At 11:53 UTC, the Parker Solar Probe reached its closest point, 3.8 million miles above the solar surface. For context, that's roughly 16 times the distance between Earth and the Moon. Which sounds like a comfortable margin until you remember it's inside the Sun's outer atmosphere, where temperatures reach into the millions of degrees. The probe was traveling at 430,000 miles per hour, faster than any object humanity has ever built. And then, silence. No signal. Just the knowledge that a spacecraft the size of a small car was threading through conditions that should, by most intuitive measures, destroy it entirely. The first beacon arrived on December 26th, 2 days later, confirming survival. But the actual science data, the readings from instruments operating directly inside the corona, didn't arrive until January 1st, 2025. 8 days of not knowing what it found. So here's the question that makes this more than an engineering achievement. What was Parker actually measuring out there? Because whatever it recorded threatens to rewrite something fundamental. A problem that has frustrated physicists for over 70 years. The paradox that broke physics. That silence on Christmas morning wasn't just engineering suspense. It was 70 years of physics holding its breath. Because what Parker flew into, what it was built to survive long enough to actually measure, is a paradox so clean, so almost insulting in its simplicity, that generations of astrophysicists have stared at it and come up empty. Here it is. The Sun's visible surface, the photosphere, burns at around 10,000 degrees Fahrenheit. Brutal, obviously. But then you move away from it, further from the energy source, and the temperature doesn't drop. It explodes. The corona, the Sun's outer atmosphere stretching millions of miles into space, reaches temperatures above 2 million degrees Fahrenheit. That's not a rounding error. That's roughly 150 times hotter than the surface beneath it. Think about standing near a bonfire, 10 feet away, warmer, 100 feet away, cooler, 1,000 feet away, somehow inexplicably. The air is 150 times hotter than the fire itself. That's what the Sun is doing. Every single second. And this isn't just counterintuitive. It's technically illegal. The second law of thermodynamics, one of the most rigorously tested principles in all of physics, states that heat flows from hot regions toward cooler ones, not the reverse. Energy from the Sun's core should radiate outward and diminish. The corona should be cooler than the photosphere. Full stop. Physicists have a word for situations like this: problematic, which is their polite way of saying the universe appears to be cheating. So what's driving it? There has to be a non-thermal energy transport mechanism, something injecting enormous amounts of energy into the corona that bypasses the usual rules. Magnetic fields are the prime suspect, but suspecting something and measuring it directly inside the actual corona are two entirely different things, which is exactly what Parker was built to do. And what's at stake isn't just academic curiosity, because the corona doesn't just sit there, it moves. Solar wind and the stakes. That mystery, whatever is superheating the corona to 2 million degrees, doesn't stay up there. It escapes. The corona bleeds continuously outward in every direction, a torrent of charged particles streaming away from the sun at speeds between 200 and 500 miles per second. That's the solar wind, an actual flow of plasma, electrons, protons, alpha particles, crossing 93 million miles between the sun and Earth in roughly 3 to 4 days. Here's where this stops being astronomy and starts being infrastructure. When that plasma stream hits Earth's magnetic field, it distorts it. On calm days, the interaction is gentle, the kind that paints auroras across polar skies. But when the solar wind carries a coronal mass ejection, a billion-ton plasma cloud launched by magnetic eruption, the results are something else entirely. Geomagnetic storms that knock out GPS accuracy by tens of meters, radio blackouts across entire hemispheres, voltage spikes surging through power grids. In 1989, a single geomagnetic storm collapsed Quebec's entire electrical grid in 90 seconds, leaving 6 million people without power for 9 hours. 90 seconds. A microwave takes longer to reheat coffee. So the coronal heating paradox isn't an abstract puzzle for physicists to argue over at conferences. It is the engine driving everything downstream. Understand why the corona reaches those temperatures, understand what accelerates the solar wind, and you can predict these events days earlier. Enough warning to protect satellites, reroute flight paths, and keep the lights on. The stakes are utterly concrete. But here's the twist. The person who first predicted the solar wind's existence had his paper rejected as nonsense. The man behind the name. That prediction, the solar wind itself, came from a 31-year-old physicist named Eugene Parker, writing at the University of Chicago in 1958. Parker had done the mathematics carefully. His equations described a continuous stream of charged particles flowing outward from the sun in all directions, driven by the corona's extreme pressure differential against the near vacuum of interplanetary space. He called it the solar wind and submitted his paper to the Astrophysical Journal. The reviewers called it nonsense. 2 separate referees recommended rejection, arguing the idea contradicted established thinking about interplanetary space, which most scientists assumed was essentially empty and still. But what makes this story special is what happened next. Subramanian Chandrasekhar, the journal's editor and a future Nobel laureate, read the paper personally. He found no mathematical error, not one. So he overruled both reviewers and published it anyway. 2 years later, NASA's Mariner 2 flew past Venus and confirmed the solar wind exactly as Parker's equations predicted. The nonsense became consensus almost overnight. Decades passed. Then, in 2017, NASA made a decision with no precedent in its history, naming a mission after a living scientist, Parker Solar Probe. Eugene Parker attended the 2018 launch at Cape Canaveral. He was 91 years old, watching a spacecraft bearing his name climb toward the star he had theorized about his entire career. The question now was whether that spacecraft could actually survive long enough to answer what Parker himself never could. 66 years of engineering, surviving the launch was one thing. Surviving the sun was an engineering problem that had been sitting unsolved for 66 years. The National Academy of Sciences first floated the idea in 1958. The same year, Parker submitted his solar wind paper. A solar probe, they proposed, one that could pass inside Mercury's orbit and sample the particles and fields close to the source. The concept was elegant. The execution was, for decades, simply impossible. As APL Mission Systems engineer John Wurzburger put it, the space science community spent those decades not abandoning the idea, but slowly advancing the technology needed to make it survivable. So what was the wall? Heat. Straightforwardly, brutally, heat. At closest approach, the front face of the spacecraft meets temperatures around 1,600 to 1,700 degrees Fahrenheit, roughly the temperature of molten iron. The heat shield was tested to withstand up to 2,500 degrees Fahrenheit, giving the mission its safety margin against the unpredictable surges a star tends to produce. But here's what that engineering actually had to achieve. While the sun-facing surface baked at over 1,600 degrees, the instruments sitting just behind the shield needed to operate near room temperature, approximately 85 degrees Fahrenheit. That is a temperature difference of roughly 1,500 degrees across a barrier less than 5 inches thick. The solution was a carbon-composite foam sandwiched between two carbon fiber face sheets. Lightweight, incredibly strong, and almost completely unwilling to conduct heat. The foam is mostly air. It is, essentially, a sophisticated nothing, and that nothing is what makes everything else possible. And what this shield unlocked wasn't just survival. It opened up an entirely new question. How do you actually get a spacecraft close enough, repeatedly, to collect meaningful data? The heat shield handles the temperature. Getting there at all required a completely different kind of ingenuity. Gravity as the engine. So, the heat shield solves one problem. But getting Parker close enough to use it, repeatedly, on a tightening spiral toward the Sun, required solving a completely different puzzle in orbital mechanics. Here is the paradox. To get closer to the Sun, you cannot simply point a rocket at it and accelerate. Counterintuitively, you need to slow down. Earth orbits the Sun at roughly 67,000 miles per hour, and Parker launched carrying that same orbital momentum. Shedding enough of it to fall into a tight solar orbit would require more fuel than any rocket ever built could carry. The math simply does not work. So engineers turned to Venus. Not once, 7 times over 7 years. Each Venus flyby is essentially a controlled theft of orbital energy. Parker swings behind the planet. Venus's gravity pulls the spacecraft slightly backward relative to its solar orbit, and Parker exits the encounter slower and on a tighter path around the Sun. Think of it like dragging a brake pad against a spinning wheel, except the brake pad is an entire planet and the wheel is a spacecraft falling toward a star. The first flyby dropped Parker's closest approach from 15 million miles to around 14 million. By the 7th, completed in late 2024, that distance had compressed to 3.8 million miles, a reduction of roughly 75%, achieved purely through borrowed gravity rather than brute propulsion. No rocket could have replicated that progression. Each closer pass put Parker inside regions of the solar atmosphere that no instrument had ever directly sampled before. Inside the corona. So Parker has spent 7 years falling inward, using Venus as a brake, arriving at a place no instrument has ever been. The question now is, what did it actually find there? The first thing to understand is that entering the corona isn't like crossing a clean boundary. It's more like walking into a room where every physical assumption you brought with you turns out to be wrong. Pressure, temperature, magnetic behavior. None of it behaves the way models built from 93 million miles away predicted. The data from closest approach made that immediately obvious. Start with the magnetic switchbacks. These are sudden, violent reversals in the direction of the solar magnetic field. The field flips back on itself, spikes in intensity, then snaps forward again, all within seconds. Scientists had detected hints of them from farther out, but assumed they smoothed out closer to the sun, worn down by the journey. What Parker recorded was the opposite. Inside 5 million miles, switchbacks become more frequent, more abrupt, more energetic. They're not fading, they're the source. The solar wind isn't just carrying these structures outward from somewhere else. It appears to be generating them right here, in the very region Parker is now sampling directly. That distinction matters enormously because it shifts the entire question of what's driving solar wind acceleration. Now, the dust-free zone. Theory had long predicted that solar radiation pressure and sublimation would vaporize interplanetary dust particles near the Sun, creating a region scrubbed clean of the material that fills the rest of the solar system. Parker confirmed it. Beginning around 5 million miles out, dust density drops sharply. A clean room in space, essentially, though considerably warmer than any clean room an engineer has ever worked in. This boundary aligns closely with where the solar wind transitions from subsonic to supersonic flow, which is probably not a coincidence. But what makes this data irreplaceable is the direct sampling of the acceleration zone itself. Every previous measurement of the solar wind caught it after the fact, already fast, structured, and far from where it became what it is. Parker's instruments collected particles and field readings from inside the zone, where that acceleration is actively happening. The wind isn't fully formed yet, it's mid-process. That is the first time in human history that has been possible. And what those readings reveal about the mechanism driving all of it leads directly into the most contested question the data now answers. The heating problem, answered. So here is where 6 decades of theory meets 60 gigabytes of reality. For most of the 20th century, the coronal heating problem was a blackboard argument. Theorists had 2 leading candidates. The first, Alf-Venn waves, oscillations that travel along magnetic field lines like vibrations along a guitar string, carrying energy up from the surface and dumping it into the corona through turbulent dissipation. The second, magnetic reconnection, the process where oppositely directed field lines snap together, releasing stored energy as sudden, explosive heat bursts. Both mechanisms were mathematically elegant. Neither had ever been confirmed by instruments sitting inside the corona while it was actually happening. That distinction matters more than it sounds. Theoretical models are built from boundary conditions, from what the solar wind looks like once it has already escaped, already cooled, already traveled millions of miles. You are essentially reconstructing a car crash from the skid marks on the highway, not from sensors mounted inside the vehicle during impact. Parker changed that entirely. What the probe's instruments recorded near closest approach, field strengths reaching hundreds of nanoteslas, extraordinarily intense for open space, showed Alf-Venn wave turbulence operating at a scale and frequency that prior remote observations had badly underestimated. The waves are not a gentle background hum. They are violent, overlapping, and energetically significant enough to account for a meaningful fraction of the coronal temperature budget. The numbers, when fed back into theoretical models, close the gap in ways that remote sensing simply could not. But what the data also showed, and this is the part that genuinely surprised the team, is that magnetic reconnection events are not rare punctuation marks on an otherwise smooth process. They are constant. The magnetic switchbacks recorded throughout Parker's inner passes appear to be surface signatures of reconnection, firing repeatedly across small spatial scales. Think of it less like lightning strikes during a storm, and more like a constantly sparking electrical grid. Nobody designing power infrastructure wants that, but the sun apparently does not care about grid reliability. So the answer emerging from the data is not one mechanism or the other. It is both, operating simultaneously, reinforcing each other at scales no prior model had the resolution to capture. That is not just a refinement of the old picture. It is a structural replacement of it. And what that replacement now makes possible, in terms of prediction, preparation, and the next generation of missions, is where this story goes next. What changes from here? So the picture that has now replaced the old theoretical model is not just academically cleaner, it has direct, practical weight. The most immediate downstream consequence is space weather forecasting. Current prediction models treat the solar wind as something of a blunt instrument, a general flow with occasional violent outbursts. What Parker's in situ data reveals is that the wind has architecture, switchbacks, reconnection events, acceleration signatures, all of them structured, all of them potentially trackable. That means forecasters can, for the first time, begin building predictive frameworks grounded in observed mechanism rather than statistical approximation. The difference between those two approaches is roughly the difference between guessing tomorrow's weather by looking at a calendar month and actually reading a barometer. And Parker is not working alone now. ESA's solar orbiter is cross-checking the same solar environment from a different orbital inclination, a second vantage point on the same phenomena, watching the sun's higher latitudes in ways Parker's trajectory never could. Where Parker goes deep and fast, Solar Orbiter goes wide and tilted. Together they function less like competing missions and more like stereo speakers, each adding a dimension the other cannot supply alone. The cross-referencing of their datasets is already narrowing the margin on models that either instrument alone could not constrain. But what really makes this moment significant is what it unlocks for the 2030s. Parker's findings have effectively handed mission planners a validated target list, proposed concepts, closer solar sentinels, dedicated reconnection mappers, even crude vicinity observation platforms now have empirical anchor points where before they had only theoretical motivation. That changes funding conversations. It changes engineering briefs. It changes what counts as a reasonable risk. Eugene Parker proposed that the sun breathes. We spent 66 years building the instruments to confirm it. Now the question is what we build next, and how fast we can get there before the sun surprises us first. The coronal heating paradox, heat flowing the wrong way, is still not fully solved. Parker's data narrows the suspects, but the verdict isn't in. Future close passes continue through 2025. The answer, when it finally arrives, will have been 67 years in the making. That's worth watching.